mean, there's still a few more minutes, right?
Yeah.
Okay.
Yeah, I started now because I'm going to forget about it and don't have a problem.
And then 10, 15 minutes into the talk, oh, Elliot, we'll have to start over.
Why can't I see the chat at the same time now? Let's try this again. Oh well.
I think it does show you notifications when you have something in the chat, but it doesn't show the chat itself.
It's weird.
Yeah.
No, I think there is an option to select chat and it will going to pop up in a different window, in a smaller window.
Yeah, so I think it's at the top, not at the bottom in the extra options.
For me, it pops up, but then when I go back to my presentation, it the window somehow gets covered up.
Oh, okay.
Whatever, I'll check up on it periodically or something.
Okay, so we started?
If you like.
Yeah, okay, as more people are joining.
There are still people constantly coming in, so maybe let's wait a couple of minutes for that to stabilize. Yeah.
Let's wait 2 more minutes, sure.
So Yucheng has joined. Should we have him try doing the screen sharing, or I guess now we can
Let's
just
do
try?
it afterwards. Yeah, let's do it.
Okay, yeah.
We'll do it
sure.
after in the break.
Yeah. In the break.
Do this.
I think we can start the introduction now.
Okay, so hi everyone again. Welcome to the second day of the Diet Workshop. We have some very interesting talks today lined up as well. And before we start with the introduction to Elliot's talk, let me just mention some things again that we also mentioned yesterday. So throughout the presentations, if you could kindly have your microphones muted, that would be great. If you have any questions that you would like to ask during the presentation, you can ask them in the chat, but just make sure that you write question in capital letters and then type your question to make it visible enough for everyone to see. And of course, at the end of the presentations, of each presentation, there will be some time for questions, so you can raise your hand. You can then unmute your microphone and you can ask the question directly. Yeah, so this is all I had to say. And yeah, let's start with the first talk of the day. So this will be given by Elliot Anshelevich. And this will be about the distortion in the metric preference setting. This is something that we mentioned yesterday. But as I said, we didn't talk too much about this precisely because we have a very nice presentation about this topic today. And Elliot will talk about his results, also some of the most fundamental results in this setting. And actually, these sets of results happen to be the same, which is great. So go ahead, Elliot.
All right, thank you. So, okay, so let's quickly just review the basic setup in social choice. And this is something that we talked about yesterday a little bit, and see what kind of models we'll be using. Okay, so in usual voting, social choice, things like this, you have M candidates. So over here, M candidates, and let's call them A, B, C, D. And you have N voters or agents. And the voters are going to vote for the candidates, and maybe we'll select just one candidate as the winner, or maybe multiple. But let's just say we're going to select one candidate as the winner for now. So there's lots of different voting settings, but the kind of things we talked about yesterday, and we'll talk about today, is sometimes known as the utilitarian approach, meaning that the voters have actual numerical utilities or numerical costs for each alternatives. So, if I'm a voter or an agent, which I'm going to use those two terms interchangeably. So if I'm a voter, I actually have a cost for candidate A being elected. I have a different cost for candidate B being elected, different one for candidate C. So these are actual numbers saying how happy or unhappy I am with each candidate being the winner. And once you have these costs or utilities, again, for today's talk, we'll talk about costs mostly. So once you have these costs for different voters, you can start saying, okay, what is the best candidate? What is the optimum candidate that we want to win? And there could be many possible objectives. Let's look at the sort of simplest one. Again, we'll spend most of the day talking about this, just like yesterday we spent most of the day talking about this objective. So we'll say the best alternative is just the one that minimizes social cost, by which I mean just the sum of the costs of all the voters. So the outcome we want is the one so that if you sum up the costs of all the voters for this outcome, it's as small as possible. So that's our goal. And distortion is just the difference between the cost of the one we actually choose and the cost of the best one, the one that minimizes social cost. So this is a way of measuring how good of an outcome we obtain. So maybe we don't choose the optimal one. Maybe it's going to be only a factor of 3 away from optimum, and then the distortion is going to be 3, comparing the outcome we actually choose with the outcome that is the optimum one that minimizes the total sum of the costs. Okay. So it's the basic voting setup. And this is the same as was yesterday, except there's utilities instead of costs, but of course it doesn't really matter very much. The main difference today is going to be, the new thing for today is, we're going to look at voter values which lie in the metric space. So we're going to assume that these numbers, these costs, aren't arbitrary numbers, and they're not going to be things that are like unit sum or unit range like we talked about last time. What we're going to assume is they're lying in the metric space. So let's, for a few minutes, just talk about voter costs in metric spaces, where this comes from, and we'll talk about distortion afterwards. So forget about distortion for a minute. Let's talk about metric spaces for a little bit. Okay, so why would voter costs lie in the metric space? Well, you can look at something really simple to start with. This sort of standard left-right axis. Maybe these, A, B, C here are the candidates, and candidate A is pretty left-wing, candidate C is on the right, candidate B is on the somewhere near its moderate candidate. And if I'm a voter, maybe I'm over here, then who might I like the most? Maybe I will like the candidate which is the closest to me. So I would like candidate B. So I would like candidate B, because the distance from me to B is only this much. Where did this appear? Interesting. But my second favorite candidate might be candidate A, which is all the way over here. My third favorite candidate might be candidate C, which is all the way over here. So in other words, my cost for a candidate being elected is just the distance from me to that candidate. You can think of it as the ideological distance. It's how much I agree with them, and so I want the candidate that's the closest possible to me. I think this makes sense. But one dimension is kind of too constraining. A lot of people have looked at one dimension. Certainly there are a lot of people who don't feel like they fit into the standard left-right axis. There's these kind of graphs and this kind of things, and here's an XKCD comic basically saying how libertarians really like these kind of diagrams because they don't feel like they fit into this left-right single axis kind of thing. But more generally, people are complicated. A lot of people don't fit into these small dimensional spaces. You can think of a multidimensional space. In fact, this is not a new idea. If you look all the way back to the Downsian proximity model, all the way back in the 1950s, people have looked at preferences which lie in a metric space. So this is something where maybe each dimension has a different issue, and my distance in that dimension from the voter to the candidate is how much we agree on that issue. Or maybe it's something even more complicated. It's just maybe it's a 1,000-dimensional metric space where each axis doesn't even really make any sense. It's obtained from machine learning or something else. And all we know is that somehow how far away we are represents how similar we are. Just some abstract notion of similarity. And the closer we are, the more I want you to be elected, the more I want you to be the winner. So this is sometimes known as spatial preferences. And again, this has been looked at for a very long time. In fact, I'm motivating this from an ideological point of view, but you can even think of it from a different point of view. Maybe my location is my actual location in the physical space, like it's where my house is. And the candidate location is where we're thinking of putting a new post office. And I want the new post office to be close to me. So maybe, and then of course, that's a distance. So we're going to make this be pretty abstract. We're just going to assume that the voters and the candidates lie in a metric space. In fact, here it is, here's our model. The voters and the candidates lie in an arbitrary metric space. So here are these red dots are the voters, these squares are the candidates, and they're in an arbitrary metric space. Again, let me stress this, truly arbitrary, meaning that it might not be one-dimensional, it might not be 1,000-dimensional, it's an arbitrary abstract metric space. For those of you who don't know or forgotten, what is a metric space? Well, really what it means for our case is we have the triangle inequality. So it means that if you have something like, here's x, here's y, here's z, it means distance from x to z is the most distance from x to y plus y to z. That's all it means. Technically, metric space also implies symmetry. So distance x to z is the same as z to x. We don't even need that. So technically, it's like a pseudo-metric, I think is what it's called. All we're saying is that the triangle inequality is satisfied. So going directly from x to z is shorter than going x to y and then y to z. A standard notion of distance. Okay, so that's all we're assuming. Voters and candidates are points in an arbitrary, possibly very high dimensional metric space. And what does it mean? It means that each voter prefers the candidates which are closer to them. So for example, if you look at this voter over here, their favorite candidate is B because it's closest, then A is next closest and C is next closest. And their actual costs are the distances. So the cost for this voter to B is just the distance from that voter to B. The cost from to A is the distance from that voter to A. And the preferences are obtained from these distances. So this voter would prefer B to A to C. So from their perspective, B is better than A is better than C. Okay. So that's the model, is voters, candidates lie in a metric space. And again, as I mentioned last time, so the best alternative is going to be, for most of this talk, the one that minimizes the total distance. So for example, the total cost of B is the distance from all the voters to B. So it's the sum of these distances that are drawn. And so in this case, I mean, I think B is probably optimum, because if you look at the sum of distances from all the red dots to the candidates, B is the optimum one. And okay, so that's the model. The model is, we have this metric space, we have voters and we have candidates. Our goal is to find the best alternative. And of course, if that's all it is, that's very easy to do. Just look at each candidate, sum up these distances, here this distance is to B, so that's the cost of B, and take the candidate which is the smallest distance, so the smallest total cost. Just look at all of them, take the minimum, done. But the catch here, and this is the whole point of this workshop, the catch is we don't know these distances. We don't usually know these numerical values. So what do we know? And here is, again, the main message of this whole workshop. Here's the truth. This is the truth. The truth is locations of voters and candidates in the metric space. Or maybe yesterday it was numerical utilities of the voters and candidates. For today's talk, it's locations of the candidates and voters in the metric space. That's the truth. But we don't know the truth. It is not given to us. We have no idea what it is. What we're given as input is this stuff. Okay. We're just given for every voter its ordinal preferences. So every voter tells us like, okay, I like A better than B better than C. Some other voter tells us, I like B better than A better than C, and so on. So that's all we know. We don't know the truth. We only know the ordinal preferences. And we know one extra bit of information, and that is that these ordinal preferences given to us come from a metric space, meaning that the reason why, let's say, player 4 likes B better than A better than C is because B is the closest one, and A is the next closest one, and C is the next closest one. So we know these preferences came from a metric space. Okay, so that's it. And our goal was to return the best alternative, the one that minimizes cost. This is completely impossible. And this is not hard to prove. I mean, you can look at the papers, but basically the reason why it's impossible is, given these preferences as input, there might be many different, I mean, in fact, an infinite amount of different metric spaces that could have given rise to these preferences. And some of them will have A as the optimum, some of them will have B as the optimum. We cannot know which one is the optimum one unless these preferences are very, very trivial. So let's change the goal. The goal instead is going to be to, instead of finding the optimum alternative, the optimum candidate, let's return something that's close to optimum. So maybe we'll return C, which is not as good as B, which is opt, but is guaranteed to be within a small factor of optimum. It's guaranteed to be not too far. So what we want is to return something so that the total cost of it, so the total distance from everybody to it, compared to the total cost of the optimum solution, so the total distance to the optimum solution, is small. And that's what distortion is. So our goal is to return a candidate so that its total cost is close to optimum without ever knowing the actual costs, only knowing this. So that's what we want. Okay, so this is the summary of the general idea of distortion in metric spaces. We want something that has small distortion. We want something that, if we select a winner, its total distance is close to the total distance of the optimum solution. And so just to explain this notation, it's not super important, but just to explain this notation, it should be that no matter what the distance metric is, as long as it's consistent with these preferences that are given to us, it should be that the thing we select is close to optimum. So we don't know what the metric is. We can never know what the metric is. We have no idea what the metric is, except from what these preferences are. And no matter which distances are actually the truth from an infinite set of possible distances, it should be the thing we select is close to optimum always. That is the goal of finding mechanisms which minimize distortion. Okay, so that is the goal of a lot of work in this workshop, and it's the goal of this talk. Before telling you about what's known about this, I think it's good to show some examples just to see that this is possible. Okay, maybe you see immediately why this should be doable, but I think it's a little bit counterintuitive. Why only from ordinal preferences, you can actually always select something that's close to optimum, no matter what the metric is, even though you know nothing about the metric. So let's see some simple example just to illustrate why this is possible, and it's good for intuition. So simplest possible example, two candidates. Right, I mean, there's only two candidates, and let's say that there's n voters total, n minus k prefer A to B, k prefer B to A, and let's say n minus k, let's say, is bigger than k. So that's all we're given. This is the only thing we know. We don't know the actual locations of the voters or the candidates. All we know is that more than half prefer A to B. What should we do in this case? Which one should we select? Let's say we have to do deterministically. We can't randomize yet. If we do randomize, we can do something else. But let's say we have to choose one or the other. I mean, we have no information here except more than half prefer A to B. Of course, we should select A. I mean, we have to do majority voting. It's two candidates. There's really not much else you can do. So let's see what happens if we do that. So first of all, just because more than half prefer A to B does not mean that choosing A is the right thing to do. In fact, suppose that K is 1. So there's almost everybody prefers A to B, and only one person prefers B to A. Even then, B may be the optimal solution, the way we defined optimal. Because maybe everybody who prefers A to B is, right on the border between A and B. They're really indifferent. They slightly prefer A to B, but really they're tied. Well, the person who prefers B to A is right on top of B. They love B. They're really passionate about B. So then the optimal solution is B, because the indifferent people, we don't care about them. They care either A or B is fine with them. We just prefer A by epsilon. But the person who prefers B is really happy if B is chosen. So B may be the optimal solution. So as I said, just from knowing the preferences, you cannot possibly choose the optimal solution. That is impossible to do. Okay, but how badly does it, how bad is the distortion? How bad is the cost of A compared to B? So let's analyze this very quickly. I have time. So the claim is that if you use majority, distortion is at most 3 here. So choosing A, when more people prefer A, means that the cost of A is not going to be more than a factor of 3 compared to the cost of B. So it's not going to be optimum, but it's no worse than a factor of 3 way. And let's see why this is. Well, so the worst situation will happen is if maybe n over 2 plus 1, but let's just say n over 2 exactly prefer A compared to B. And then what will happen is we'll choose A because maybe n over 2 plus 1 prefer A, but let's just say it's n over 2. Or maybe we broke ties with respect to A. So what's the cost of A? So again, this is the worst case that can happen. The people who prefer A are right on the border between A and B, but the people who prefer B really, really love B. Okay, then what's the cost of this? Well, let's see. So the cost of A is going to be this. Let's say that this distance is 1, just for now. I'm being a little bit sketchy here, but this is the basic idea. So it's n over 2 times 1 plus this. So let's say this is 1 and 1, so the distance is 2, plus n over 2 times 2. So that's the cost of A. I mean, assuming that the voters actually lie where I pictured them, but just believe me, it's the worst case. So that's the cost of A. What about the cost of B? Well, the cost of B is going to be 0 for all these guys because they're right on top of B. And so it's just going to be n over 2 times 1. So what's the ratio of cost of A divided by cost of B? It's 3. So there you go. If you choose the candidate that more than half people prefer, you know for sure that that candidate might not be optimal, but it's within a factor of 3 of optimal. So it is possible for this very simple case, at least. This very simple case also shows that actually no deterministic mechanism can have distortion better than 3. And why is that? Well, suppose that you're given just this. You're given n over 2 voters prefer A to B, n over 2 voters prefer B to A. You have no information about selecting A versus B. But if it's a deterministic mechanism, you have to select one of them somehow. If you select the wrong one, distortion equals 3. So you cannot do better than 3. But for this simple example with 2 candidates, you can actually do distortion of 3. Okay, so that is the basic model, the basic idea, and I hope at least some intuition is doable here. So let's talk about what is actually known about this problem, about minimizing distortion in a metric space. And quite a lot is known at this point. So what people have done is look at lots of different voting mechanisms, common voting mechanisms, and analyze their distortion to see how good they are according to this measure. So here are some voting mechanisms from worst distortion to best distortion. For things like K approval and veto, I mean, in the paper a long time ago, I showed that, okay, it can be as bad as something that depends on the number of voters, and here's the number of voters. For plurality and border, it's a little bit better. So it's linear in the number of candidates in the worst case. Then, you know, lots of other things have been shown. For ranked pairs, it's the distortion is square root m. For a single transferable vote, it's log m. But actually, so I think this is all this is quite interesting. In fact, even in 2015, it was already known that some pretty well-known simple mechanisms known as Copeland, which if you don't know what that is, I won't get into it, but it's a very nice, elegant, well-known voting mechanism, was shown to have distortion of 5. So it was already known that you can always have a constant distortion. So again, let me say what it means. It means you only know the ordinal preferences, and you know they come from a metric space. You know nothing about a metric space. That means you can choose a candidate always, so that no matter what the metric space is, it's always within a factor of 5 of optimum, always. So this was known, but, and the lower bound, as I mentioned, was 3. But then for quite a long time, it was, there was this gap. It was unknown if you could do better than 5, or you know, if you can get to 3. And just recently, there was some amazing progress on this, starting with basically extending Copeland versions to become much more powerful, a very elegant mechanism, which was able to show a 4.23 distortion. And then finally, just this year, these nice authors were able to show a distortion of 3, finally closing this gap. So now, because of this, I would say a very impressive sort of a breakthrough result, now we know that you can actually always choose a candidate within a factor of 3 of optimum. And you cannot do better because of this lower bound. So this is pretty cool. I'm not going to talk about this result at all, because the next talk in this workshop is exactly going to be talking about this result. So you will see all of this described in detail exactly as in the next talk after mine. So this is pretty cool. So lots of things are known about it. About distortion of various mechanisms. But quite a lot of people have worked in distortion for metric spaces, not just for this basic version, for a lot of other things. And you'll see some of these talks again later today or next time as well. So here is just a few things people have worked on with respect to distortion in metric spaces. I'm not going to go through them all, and I didn't do citations here because I would forget somebody, and then you know, that would be a shame. So just to give you some sampling of what's known, and again, look at other talks in this workshop as well. So people have looked at distortion of truthful voting rules, and they looked at other objectives, like instead of the total cost, the total sum of costs, they looked at things like median costs, other fairness properties. They looked at candidates being drawn from a population of voters. They looked at various distributions of voters and how distortion changes then. They looked at different levels of knowledge. So maybe, what if you know the candidate locations, but not the voter locations? What if you know approximate distances? What if you know less? What if you know less than the full ranking? Trade-offs between how much you know and distortion, and lots of other things. So again, I'm not going to go through all of these because a lot of stuff is known about this, and you'll see some of this later in the workshop as well. So that's what's known. But I mean, what I don't like in these kind of talks is, okay, here's lots of stuff that's known. I also want to talk about some things that are not known, because especially if you're somebody who hasn't really looked at this before, it might be interesting for you to know what's still open in case you are interested in working on this stuff. So let me talk a little bit about what is still open in this basic distortion in the metric space setting. So here's some open problems. I'll only mention a few. Maybe I'll talk about a few others at the end, but for now I'll mention a few. Okay, so first of all, committee elections, by which I just mean multiple winners. So what if instead of electing a single candidate, you're electing K candidates? Well, here it depends on the objective. So if the cost of a voter, so let's say we elect these 3 candidates. If the cost of a voter is their sum of the costs to all of them, then you can basically do the same techniques to show it's still distortion is small, so 3. But if you're looking at something like a K-median objective, meaning that the cost of a voter is just their distance to the closest of the elected candidates. So meaning like, we're electing a committee, what I want is, I want there to be at least one representative that's close to me. That's my objective. That's, as far as I know, for this basic metric problem, is still totally open. It's not clear how to come up with something that's good distortion if you're electing K candidates and the objective is the distance from voter to the closest candidate. And the same thing for other objectives like maximum distance. So that would be, I think, a pretty interesting thing to think about. And again, I don't know the answer for this one. The other, I think, big open problem direction is randomized mechanisms. So let me talk about this for, like 5 minutes, maybe 10 minutes. We'll see how much time I have. So here's what is known for randomized mechanisms. So it's so randomized dictatorship, which is just the simplest randomized mechanism you can get. And so what is randomized dictatorship? Is just choose a voter at random, and then elect the candidate that is their favorite. That's randomized dictatorship. So you choose a random voter, and then make them be the dictator, and they're the ones who elect. This is known to have a distortion of 3. And this was proven in 2016, but actually this is already known even in 2012. It wasn't really proved for this distortion setting, but it was already known that randomized dictatorship has approximation factor of 3 here. So this was quite well known. Lower bound for randomized mechanisms is 2. For deterministic mechanisms, we saw lower bound is 3, right? But for randomized mechanisms, lower bound is 2. So nothing can do better than distortion 2. That's also pretty easy to show. And for something like truthful mechanisms, or mechanisms that only know the top choice instead of the full ranking, so you're only given the top choice of every voter instead of their full ranking, it can be shown that 3 is tight. But there's still a gap between 3 and 2 in general. So it's completely unknown here whether you can always design a randomized mechanism which in expectation gives distortion of 2. So this is definitely a gap that's be pretty interesting to close and is currently unknown. So, okay, so what I think I want to do next is, so what I want to do for the rest of the talk is, first of all, I want to talk about some other problems beyond voting and distortion in those problems. But I also want to spend a little bit of time giving you an idea of how these distortion proofs are done, at least at a very high level. And so what I think I want to do for the next 5 minutes or so is actually try to prove to you that randomized dictatorship actually has distortion 3. Just to give you a basic idea of how these distortion proofs work at a high level. And if you're interested, great. If you're not interested, okay, then I'll start with high-level stuff again 5 minutes from now. So let me try to actually prove to you why randomized dictatorship has distortion of 3. So the goal is going to be the following. We're going to want to charge this amount. This is the expected cost of randomized dictatorship. So let me say what this means. A sub I here is the candidate, which is the favorite the closest one to voter I. Right? Each voter I is chosen of probability 1 over n. There are n voters, so each one is chosen of probability 1 over n. And so probability 1 over n, we choose the candidate which is the favorite, the closest to voter I. And so this is the total expectation of randomized dictatorship. So for each voter I, look at their closest one, that one's chosen of probability 1 over n. We want to show that this is, at most, 3 times the cost of B, where B is an arbitrary candidate. For example, it could be optimal. So we want to charge this cost to this cost. Now, when we do this charging, here's something important to realize about these distortion proofs and distortion arguments. We really know very little that we can use in our proofs. We really only know 2 things, and those are the only 2 things we can use to prove things. Now, using those 2 things, we can come up with amazing arguments, really deep stuff, as you'll see like in the next talk. But at the very basic level, these are the only 2 things we know, and so these are the only 2 things we can use in the proofs. So here's what we know. We know that if I prefers A over B, that means the distance from I to A is smaller than distance from I to B. I mean, that's the definition of saying preferences came from a metric space. So I prefer candidates that are closest over candidates that are farther. Okay, so we know that. So it means that we can charge like the distance from I to A, this red arrow, we can charge it to distance from I to B, because we know that's going to be bigger. The other thing we know is the triangle inequality. And the triangle inequality, as I mentioned, is just this triangle thing. But actually, here we only really care about distances between voters and candidates. We don't really care about distances between voters and voters, or candidates and candidates. We can't really use that so much. So triangle inequality means that distance from I to A is at most this plus this plus this. Right? Because taking a shortcut is always should be better than going the long way around. That's what metric space means. That's what triangle inequality means. So that's what we know. So we know we can charge this red arrow to these 3 blue arrows, where J is an arbitrary other voter. Those are the only 2 things we know. So let's see how we can use those 2 things to actually prove randomized dictatorship has distortion 3. Okay, so here's the idea. Let's look at the cost of AI. So the cost of a favorite candidate of voter I. So what is this? Well, we know nothing about this cost, except that voter I prefers AI to everything else, right? Because it's the favorite of voter I. So what is cost of AI? It's distance from I to A, plus the distance of everybody else, all the other J's. So here's like J not equal to I. So all the other J's to A. That's the cost of AI. And somehow we want to charge that to the cost of B, to the distance from those voters to B. Okay, so let's see what we can do. Well, first thing we can do is, let's use the triangle inequality. Again, these are the only 2 things we can do. So let's use triangle inequality. And so what we do is, we can charge this cost of J to A, we can charge it to this, plus this, plus this. And for this other J, we can charge it to this, plus this, plus this. We do this for every J, so what do we get? We get the distance from J to B once, distance between I and B, n minus 1 times, once for each J, and the distance from I to AI, n times, 1 for each J, plus the 1 time that from I to A that was already there. So that's what we get. The costs from J to AI have been charged to this, plus this, plus this for each one. And so instead of this red stuff, we get this blue stuff. So cost of AI is at most n times this distance, plus n minus 1 times this distance, plus 1 times each of these distances. All we did was use triangle inequality. Okay. Now let's use the other thing we know. If I prefers AI to B, that means this distance is smaller than this distance. That's what preferring means. So let's charge this to here. Great. So we charge the total cost of from everybody to A. So all of his cost. We've now shown it's at most 1 times each of these, plus 2n minus 1 times this. We did it just by charging this distance, n to this one, and so we get n minus 1 plus n, that's 2n minus 1. So now, by just using these two super simple things, triangle inequality and the fact that if I prefer A over B, then distance from I to A is smaller than distance from I to B, we get that the total cost of AI is at most something that's talking about distances from voters to B. And we're done. Let's just sum this up over all AIs. So what do we get? We get distance from each voter to B. How many times does that occur? It occurs 2n minus 1 times when we chose that voter in randomized dictatorship, and it occurs 1 time for every other voter. So it's 2n minus 1 plus n minus 1. So we get the total cost of sum of AIs, at most 3n minus 2 times the total cost of 2b. Just use, again, I'm going pretty fast, but I'm hoping you see the general idea is that we're just using these two simple things in a very straightforward way. And now we're done, because randomized dictatorship is just 1 over n times this. And so the total distortion is just this divided by n. So in fact, we even get something better than 3. We get 3 minus 2 over n here. So the total distortion of randomized dictatorship is 3 minus 2 over n. Just by using this argument of looking at the cost of randomized dictatorship and using those two simple things to rearrange the costs. Okay, so that's the basic, that's all I really wanted to say about this. The point is that, great, for randomized dictatorship, this is not too hard, but are there better mechanisms? We're using this kind of insights, using these kind of rearrangements, you can get a better distortion. The only lower bound we know is 2. Can you actually get a more impressive mechanism that will give us distortion of 2? Okay. That's pretty much all I'm going to say about voting and social choice. I have about 15, 20 more minutes. So what I want to do is quickly talk about some other problems that people have looked at in terms of distortion. So distortion beyond social choice. And there's been quite a few problems. Some of them I won't mention, but some of the problems we have looked at is, including myself, is matching problems, facility location problems, and other graph problems in general. So let me talk about this for just a little bit. So let me start with another introduction, because this will be a slightly different direction. So let's talk for, again, 5 minutes about maximum utility matching. So this will be a little bit different from the first part of the talk, because we're doing utilities, not costs. So here is, here's a graph. The edges have weights, and we want to form a matching of maximum weight. For example, in this, in this graph, this and this would have maximum weight, 90 plus 90. So what do the weights represent? Maybe the nodes are students, and we're trying to break them up into teams of 2 from partnerships, and the weight is like how well they work together. This is the grade they'll get. So if A and B work together, they'll get 100. If A and C work together, they'll only get 90. And the goal is to maybe break them up so that the total weight is as high as possible, something like that. So that's our goal. It's maximize social welfare. Again, we could look at other goals, and people do look at other goals. But let's say our goal is just to maximize the total weight of the matching. So the total utility, the total weight of edges selected. That's a great goal. People know how to find maximum weight matching. It's a classic graph problem. So what's the difference in this workshop compared to general graph problems? The difference is, what if we don't know the weights? What if we only know ordinal preference information? So this is, again, the truth, and this is what we know. We know that student A, they're not going to tell us, if I work with B, I get 100. If I work with C, I get 90. All they say, I prefer to work with B over C over D. You don't know how much they prefer. All you know is that they prefer it. So then, based on this, just based on what we know, we're supposed to find the maximum weight matching. Again, this is impossible. Why? Because let's say we're given, this stuff on the right. what could be the true graph? It could be this one, in which case maximum weight matching is 90 and 90, or it could be this. Both of these weights lead to the same preferences, but in the first one, the maximum weight matching is 90 and 90. In the second one, the maximum weight matching is 101. But we don't know which one it is, because we don't know the weights of the preferences. We only know the ordinal information. But once again, just like in all the other problems in this workshop, just like in voting, we can approximate the maximum utility matching using only this ordinal information and nothing else, which is pretty amazing. In fact, for matching, it's not too hard to do. So let me tell you why. So here is an algorithm for matching. It's a very nice, simple algorithm. Okay, look at the rankings we're given. It's these rankings right here. Are there two people who prefer each other as their first choice? So like, are there two people who just absolutely love each other? They're each other's first choice. The answer is yes. In fact, there always has to be. There always has to be yes. If these weights are symmetric, that has to be yes. So in this case, A and B prefer each other. Like A's first choice is B, B's first choice is A. So let's just take that edge and look at and then remove them from the graph and look at the rest. Are there two people in the rest who prefer each other as the first choice? Well, yes, there are. C and D didn't like each other, but they're the only ones left. So they're each other's first choice. So just have them take each other. So it's a greedy algorithm, completely greedy algorithm. Just find two people who prefer each other as their first choice and match them. That's guaranteed to give a factor of 2. And this is basically based on a classic algorithm where you just take the highest weight edge, take that, repeat. This is a 2 approximation to the optimum maximum weight matching. If you didn't know this, it's a good exercise for like a basic graph for algorithms class or approximation algorithms class. And this algorithm is technically not ordinal because I don't know which edge has maximum weight. I don't know their weights. But this other algorithm I mentioned, which you just take an edge so that X and Y are each other's first choice, that's ordinal. And you can show using the same argument, it produces a 2 approximation to the optimum matching. So here you can find a matching which is factor of 2 away from optimum, no matter what, only by knowing ordinal information. So that's great. Notice I did not say anything about metric spaces here. This is true even if these weights are completely arbitrary. They have to be symmetric, like the weight of the edge A to B instead of, it should be the same as B to A. But other than that, you don't need a metric space. You can already do a distortion of 2. Now, what if you do have a metric? Then you can do better, not surprisingly, because it gives you more structure. You can actually do a 1.6 approximation instead of 2. And the lower bound is 1.25. I'm not going to go through this given the time we have. So basically, okay, so let me just skip some of this. So basically, yeah, you do some, use this greedy idea of taking highest weights edges, and you look at the random matching, and then you mix over them a little bit and do something slightly. It's not too hard, but you can get a 1.6 approximation. Since it's getting late, let me get to the sort of summary of other graph problems rather than going over another algorithm. So here is most of the things that I know about distortion of different graph problems. So maximum weight matching, as I just mentioned, if you know the edge weights, you can get a 1.6 approximation if the edge weights come from a metric space, if they're assumed to they have a triangle inequality. If they don't, again, you can actually do a factor of 2, even if it's not a metric, which is pretty cool. So this is, so this column is what you can do if you know the exact weights. So this is how well you can do in polynomial time if you if you knew the exact weights, if you have full information. So this is what you have to compete with. And this over here is how well you can do it if you only know ordinal information, only know the preferences. So maximum weight bipartite matching, you can only do this much, so I should probably explain this. Bipartite matching shouldn't be much worse. So what I mean by bipartite matching here is you only know the preferences of one of the two sides. So here, there's no sides. You know the preferences of every node for every other node. Which one is my favorite? Which one is my second favorite? But here, what I mean by this is you only know the preferences of one of the two sides of the bipartite graph for the other. And so there, you can't do as well, but you can get like a 1 plus square root of 2, which is what this number is, distortion. And there's lots of other problems, which I'm not going to get too much into it. These are NP-hard problems, so the best we can do is these 2 approximations or 2.88 approximations. Or here's max metric traveling salesperson. The best known approximation is like 1.14. If you only know ordinal preferences over the edges, you can do like a 1.88 approximation. Some of these you can do even if without having a metrics. For example, next planar subgraph, you can get a 4 distortion even without it being a metric space. But that's pretty cool. So this is and there's also results on things like what if you're looking at truthful mechanisms and so on. So again, the punchline here is kind of lots of things are known, and before I get to the end of the talk, let me again talk about some things that are not known, just so I don't give you the impression that everything has been studied. So here are a few things that are not known. Let me start with the last two actually. So some things that are not known is for this maximum weight matching. Again, we have this upper bound of 1.6, and the lower bound is 1.25. So again, there's a gap. There might be much better approximation algorithms, much better algorithms that only use ordinal information to come up with good solutions. We don't know. In fact, it's even open for deterministic mechanisms. For this one, this max weight bipartite matching. So this 1 plus square root of 2 came from, again, randomized dictatorship, randomized serial dictatorship, actually, where you just take one agent, one node at a time, and then just take their best choice, then remove it from the graph, take another node randomly, take their best choice, remove it from the graph. So this basic idea, the same greedy kind of algorithm that I was talking about before, that gives you 1 plus square root of 2. But first of all, there might be better mechanisms. Second of all, even for this very simple mechanism, randomized serial dictatorship, it is not known whether this analysis is tight. It might be that just that super simple greedy algorithm gives you a factor of 2 here. We don't know. So there's plenty of open questions and gaps here. But I would say the main open question for this graph problem is this. So here's something that I kind of sketched over and tried to trick you maybe a little bit. If you look at all these problems, these are all maximization problems. Unlike the first half of the talk, where I talked about minimizing the cost, the distance from agents to a candidate, these are all maximized utility problems. So you're given a graph and you want to maximize the weight of the matching, for example. Now, there are times when having a metric maximization problem makes sense. There's some nice applications of it. But usually, having a minimization problem with metric makes sense. So what about minimum cost matching in a metric space? So in a metric space. So let me just say what I mean by this problem so it's clear. So you have a graph. It obeys the triangle inequality. And your goal is to find a small cost matching as possible, minimum cost matching. But for every node, you don't know the weight of the edges. You only know that this node says this is the cheapest edge, this is the next cheapest edge, and so on. So we only know the ordering of the edges. We don't know the actual weight of the edges. Can you find a good matching? This, again, as far as I know, is truly open in the sense that the best upper bound in distortion is linear in n, the number of nodes here. But there's no non-trivial lower bound. Like the best lower bound you can come up with is just, look at basically 4 nodes or something and get from that, and it's a constant. I mean, there's lots of good ideas here, but somehow it's a much more difficult problem than expected. Looking at this and thinking about this for a few weeks, I think the correct answer is something like log n, but it certainly doesn't seem obvious, and this is something that would be very interesting to think about. Okay, so I'm pretty much out of time, so let me just conclude by saying, okay, so I tried to tell you about these distortion problems in graph problems, like here. So this is if you have a graph problem, but you only know the ordering of, or maybe even local ordering of the edges, because each node tells you the ordering of the edges next to it. But most of this talk was really about social choice, right? And these were some of the open problems that we talked about in social choice, where the goal is just to select a single candidate that minimizes or gets close to minimizing the total distance from all the orders to it. And we talked about various problems in that. And in the next talk, you'll see, and it's an amazing result on this, but still quite a lot of things are open, including randomized, tight randomized bounds, as well as committee formation. And I think, okay, that's where I'm going to stop. And I see there are questions.